Okay, students, last time we discussed the basics of geometric transformation. We saw the image scaling, like shrinking or zooming of the images, and then we saw the rotation and translation of images. And today we will start the, we will keep progressing further in this track. Here it was translation. So one thing I think I mentioned somewhere. So there are two types of transformation functions. There was one thing I think maybe I didn't mention is this thing that the translation, it normally or preserves or saves or does not disturb the orientation of the image. So if the image, I think I discussed it. So if the image is like this straight, it may change to another location, but it will remain straight. So both of them, the previous one also, the shrinking or zooming of the image will also not disturb the orientation of the image. Maybe the image becomes big, but its angle will not change, its rotation will not change. That is called the orientation. Okay, orientation will be preserved in translation and also in zooming and shrinking of images. Very important, you should know this, and also for your exam also. So rotation is another method. We have already seen this, and this is how to get the rotation matrix. So these things that we have studied till now, these four of them, they are called together as the similarity transforms. The translation, rotation, scaling. Okay. So these these three things are called similarity transform. These transforms, they normally change the image, but in a similar axis or in the similar context. So they are not changing too much that image. There is a concept over here that is used called as the degree of freedom, DOF. Now, what is degree of freedom? If some of you have taken a short course on the robotics, they will definitely know this. So, degree of freedom, mm, for example, it means that how normally degree of freedom is a term that is used in the case of robotics, for example, that if there is a small robotic arm and it can rotate, and it is tied to from one corner and it can rotate like this, up or down. Okay, so normally the degree of freedom is the term that is used when we say that for this robotic arm it has 1 degree of freedom because it can have only one type of movement. So in one direction only it can move. So degree of freedom is associated with the number of directions that something can move in. So robotic arm, if it can move only up down, then it has one direction of movement. But if it can move in up down, okay, and also it can move maybe left or right, okay. So left, right, and up down, these now are 2 degrees of freedom. Two directions are there that it can freely move in. Okay. So degrees of freedom are in normal XY plane. You can have up, down, left, right. There is one more thing that is possible. Sometimes it is there for some robotic arms. It is forward or backward. So practically three types of degrees of freedom are possible when you want to move something. So you want to move an object, you can move it up, down, left, right, forward, backward. So let's say you have a small book in your hand. So now for the movement of this book, how many places you can move it on? So you can move it on up, down, left, right, and forward backward. So there are basically 3 degrees of freedom. Up down will be counted as 1, okay, because up and down they are same thing, just the magnitude, you put a negative sign. For example, you are going up, you maybe count it as positive movement. You go down, you count it as a negative movement, but it is basically same thing, okay. And similarly, left right they will be considered one movement, and also forward and backward it's a one movement, okay. So these are the 3 movements. Now let's say I give you a question. Let's say that there is a book. I place it on the tabletop. So the book is on the tabletop. What you think that this book, how many degrees of freedom it will have? Okay, from in which directions you can move it. So I tell you that it's on the table. You can't pick it from the table. It will remain on the table. So in that case, it will have 2 degrees of freedom. Left, right, forward, backward. No up or down. Okay. So degrees of freedom, they can be in the form of movement. So these are related to movement or displacement. Okay. Movement related degrees of freedom, they are like in directions of x, y or z axis. Clear? There is another degree of freedom possible, which is related to angles. So this was related to movement. There is another one that is possible related to angles or rotation. So if I say that instead of that robotic arm that was moving up or down, I say that there is a motor. All of you know a motor. And motor, it is not moving anywhere. It is very powerful motor, but it rotates. Circle. So rotation is also a movement, yes? So rotation, what does it mean? Rotation does not take it anywhere. Rotation is not something that you measure like the normal XYZ. Because in XYZ movement, you measure the distance, how much you move. Whereas in rotation, it is around in a circle, around an axis, center point. So rotation, when we want to know, this is one type of degree of freedom. Rotation. Now the rotation is done, for example, in x-axis like this, around the x-axis. The axis is x. Or a rotation is done, for example, around the y-axis. So if there is a rotation over here like this, so this is the motor shaft. Now it is rotating like this. That is another one, another degree of freedom. So again, just like before, now we will have another one also, which I'm not so good at drawing. This will be the z-axis, and the motor can rotate around its axis, around its center point. Okay, so there can be a degree of freedom over here also. Okay, so these are 3 types of rotational movements. We will not call them x, y or z. There are specific names for them, but we will not discuss those things here. Okay, so just one more example, then I will finish it up. That is, let's take the example of a car. So for example, there a car, it has wheels. Okay, and what you think, how many degrees of freedom for the car? So car can move forward or backward. So this is 1 degree of freedom. Okay. Okay. Next, can the car move to the right or left? Yes, important question. No. For those of you who are thinking that car can move right or left, no, it's wrong. Car cannot move right or left. If it was possible, right or left movement means that the car will be moving purely in that direction. The XYZ movement says this, but car does not move purely in sideways. only the front wheels of the car, they rotate little bit, and we create a feeling of left or right movement by steering the wheel. Okay, so basically that is the rotational movement that is performed around the z-axis. Maybe you can say, if this is the center point, you put up, for example, imagine there is a pole, you put the big rod from the top to bottom of the car, so car is moving around that pole, left or right, rotating around that pole. So basically car has 2 DOF, degrees of freedom. Okay, it has 2 degrees of freedom, and one is moving forward backward, and second one is rotational, rotation around the z-axis. So car can only rotate around one of the axes, a little bit of rotation, not full rotation. Okay, wheels allow you to rotate a little bit, whereas there is no rotation at all around y and z axis. Okay, just imagine a ball. If you have a ball, you throw it in the air, how many degrees of freedom it will have? So ball will have all the three movement related or displacement related degrees of freedom, x, y, z, and ball will hopefully have all the three types of rotation also. Okay, what about a fighter plane? Not a normal commercial aeroplane, but the fighter plane, fighter jet. So fighter jet like a F-16. So how many degrees of freedom it has got? That is for you people to figure it out. You figure it out and then write it as an answer in the group. We will discuss. So this was a little bit of discussion for those who didn't already knew what is degrees of freedom. So degrees of freedom in this type of transformation that we have seen till now. So we have seen three of them: translation, rotation, and scaling. Okay. So in this type of transformation, we have 4 degrees of freedom. Okay. 4 degrees of freedom, how? So 1 degree of freedom is that you move the image, for example, or make it large in the x direction. You move the image or maybe make it large in the y direction. Okay. So image is basically 2-dimensional, so you can exploit both these dimensions. There was one more degree of freedom that is related to the rotation. You rotate it right or left, or clockwise or anti-clockwise. That is another degree of freedom. What else? Fourth one, I don't remember now. So translation, scaling. Fourth one, I don't remember. I will check if I find it somewhere. I will tell you. So 3 of them I mentioned: x, y, and the rotation, clockwise or anti-clockwise. Okay. One important thing is that this similarity transform, these 3 together, they are called similarity transforms. So similarity transform, any type of similarity transform, it preserves angles. So what does it mean, preserving angle? It will be clear when we go to the next topic. Okay. So this is one example. You can change the aspect ratio of the image also. Sometimes it happens that in all the previous cases in the similarity transform, we were making the image only modify, but we were not changing its dimensions. For example, if the image has more width over here, still the image has more width everywhere after transformation. But here is another example. If I have an image, I can skew or I can disturb its aspect ratio. So if you people have known this maybe in multimedia course, aspect ratio means the ratio between the width and the height of the image. That is called aspect ratio. So we can disturb this aspect ratio also using the transformations. Now before it was a wider image, now it has more height and less width. How it is done? It can be done by such a transformation matrix where you use one value one transformation value, for example, you use 2. On one axis you use the zooming effect, multiply by 2. On the other axis, so this is for the x-axis, for the other axis, y-axis, you use the shrinking effect. So you use 1 by 2. If it was 2 over there, here it will be half for the y-axis. So this is how you can disturb the aspect ratio. So here it is. The new position of the x prime will be equal to 2 times x, whereas the new position of y prime will be equal to y over 2. Okay. Here is another example. This is called as shear. Now this is something very different. This thing, the shear that you see over here, this will disturb the image in big manners. Aspect ratio is only changing the ratio between x and y, the width and height. Okay, so it will definitely deform the image. You see the cat was looking different over there, and here it has changed. It will deform the image or make it bad. Okay, change the form in a bad sense of the image. So that was the aspect ratio. There is one more which will also deform the image a lot. That is called shear. And in the case of shear, what happens is that not only you are disturbing the aspect ratio, but you are also changing the angle of view of the image. So as if you are viewing the image from a side. Okay, you take a photo of the image, or you take a photo from the side angle. So this can be created by such type of matrices where you have diagonal values, all the diagonal values as 1, whereas off diagonal values, non-diagonal values are some constants a and b. So if you note down here, the x prime will be equal to x plus the effect of y. So y will affect x and x will affect y. That's what is happening over here. It will be bx plus y. Okay. This type of transformation, when you have also the availability to transform, uh, change the aspect ratio of the image, or do the change the appearance of the image, but the view angle, then that will have more degrees of freedom. So you see, when you are disturbing the aspect ratio, that adds one more degree of freedom. And if you do the shear, that is just like if you rotate the image on other axis. So for example, if this is the image, just imagine you have a wire over here and you rotate the image around that wire. So it becomes like this, that as if you are rotating the image. One side is near, one side is far away. So here is also one more extra degree of freedom around the z-axis maybe. Okay. These all these transformations together they are called one group of transformation. We call them affine transform with 6 degrees of freedom. Okay. So 6 degrees of freedom are there for this. We call it affine transform. One property, so affine transform, it does not preserve angle. So that was the reason I wanted to explain it later. Similarity transform preserves angle. Angle means that the object, for example, over here has an angle with the cat, or a cat has another angle with another cat. It is in a particular ratio with another cat. That angle is disturbed. That angle is disturbed. If you look at these two images, you will see there is a change. In the aspect ratio, in the shear, it is even more disturbed. Okay. So that angle is disturbed between the image objects. That's why the images are no more original. They are deformed or modified badly. So the original similarity transforms, they preserve angle between the objects inside the image, but the affine transform, it does not respect because of these new two types of transformations, aspect ratio and shear transform. The affine transform no more preserves angles. So okay, so no angle preserving is because of these last two options, last two transformations. Okay. What thing is still preserved in this thing is that parallelism is still preserved over here in Affine transform also. Let's say you have two lines over here in original lines, they are parallel. Even if the image is transformed, they still remain parallel to each other. That is still preserved. Okay, so that remains over there for now. So affine transformations remember the important definition, and this is also for the shear and the aspect ratio, that parallel lines, they are not disturbed. Parallel lines that are in the original image, they still remain parallel in the output image. And to find out the transformation matrix, normally for affine transform, if you want to do some such transform, you will do this transformation using by finding, you to perform the affine transform, you need the transformation matrix as we did previously in other approaches. And to calculate what it is, this transformation matrix, you need the 3 points mapped between the input and the output. What does it mean? So let's say in your image over here, you map one location over here. Let's say this one, okay? And another location, maybe you map the eyes of the cat, and the third one maybe somewhere on this cat, the legs of this cat. So one particular pixel or point you will map from that image to the resulting image. For example, let's say you have an image like this one. Okay, you get it from somewhere, someone gives you this image and you want to make it correct. So for this purpose, you will mark down these points. Okay, so let's say which points you marked: the eye of the cat, okay, and the leg of this cat, and then one point was over here, I think. Okay, so 3 points you will mark over here, and you will also mark it over here on the cat. Okay, so you will mark these 3 points. You will have to give the exact location of these points, the XY location. XY location on this image. So this is your input, and this image is bad. And you will also show the location of these points on the output image. Clear? So on the output image, you will show these things, and this will the get affine transform. So it's a function in CV2. It will generate a function, it will generate a matrix for you to do this transformation. It will help for all other parts of the image. It will transform it into this correct image. Okay, so this get affine transform will create a 2 by 3 matrix for you, and you can pass this matrix to the warp affine function to do the transformation. Okay, so now let's come to the practical side. I will show you this affine transform on the chess example. So let's say here it is. Affine transform. So you see over here, in Affine transform, all the parallel lines in the original image will remain parallel in the output image. So you already know this. So to find this transformation matrix that will perform this transformation, remember why we need transformation matrix? Because the function which is called as get affine transform, it will produce the transformation matrix, and this transformation matrix is used by warp affine function. So warp affine is just like filter 2D. It takes an image, it takes the transformation matrix, and it will take the output size and it will transform the image into the output. Okay, so how it works? So this is my image, I load it, and then what I do is the next step, I will mark down 3 points over here on this image. So for example, for this image, I mark these points over here, these corners. The corner over here, I don't know what its value is. The second corner, this one, and the third one over here. So these 3 corners I will note down on this image. So to note it down, how to do it? I will never be sure about the exact value of the corner point. So the best way for this, what I do is normally that I make a rectangle using the lines. I take lines and I draw a rectangle all around this shape that I want to cover. So here is the code you see over here. So what it is that I use over here, I create an array, an numpy array from the points that I select. So the points are selected in this manner. First point 50, 10, it is this point. Then the second point will be this one. Okay, so it moves like this. Starting from top, it will go in anti-clockwise direction. So the second point is 5, 140, and it is this point over here. Third point is 310 and 140, and finally it is 260 and 10. Clear? So this will create a rectangle around the shape. So I want this chessboard to be correctly displayed in the new transformation style. So it should be transformed. So these are the 4 points I identify, and I just use this command over here to reshape these matrix in a proper shape. So just you use it as same, you don't need to go in details. And then I use this function which you practice somewhere in your lab, which is polylines. So to draw these, so take the image and take the array of points, and it will draw the box on the image. Okay, finally you display your image. So what does it mean? Now from this, when I draw this rectangle around the image, now I can easily find out what are the 3 corners. Now I only need 3 corners, I don't need four of them. So the corners that I selected over here, they are 50 and 10, so this one, and 5 and 140, this one, and the third one is 310 and 140. So I select these 3 corners. Okay, top left and bottom left and right are selected. So these are my initial points on the image, which is the bad image. Now when I want to do the transformation, where should they go? Now that is an important question. Okay, where should they go? This is not an easy question. Okay, so what I want to do is, let's say I can't draw over here. I can draw. No, I think I'm not allowed to draw, but I want will explain over here. So see this second point 5, 140, I would like this point to move inside and make a box like this. Okay, so I would like that these 2 points that are below, they should move inside the image so that it becomes more like a square. You see, now it is not a square. Now it is not a, sorry, not a rectangle. It's a modified shape. It's not a rectangle. So I want to make it a perfect rectangle. Only then it will look proper. So for that purpose, I will select over here 5,140. I move it towards inside and it is 50,140. So X side is changed. Similarly, on this side, I have 310,140. I move it inside. It is 260 and 140. Okay. So these are the two set of points. So 3 points in each set. I create two arrays, point 1, points 1 and points 2. So you can see over here these two arrays. And I use these two arrays to get my affine transform matrix. So I will use cv2.getAffine transform and it will give me this matrix M. Just use it and it will create a small matrix for you. The matrix, if you remember, it will be a 2 by 3 matrix. Okay, and it gives me this result. So when I apply the warp affine, cv2.warp-affine, I provide three things: image, the matrix transformation matrix M, and the output size. So output has columns and rows. The size. So it should be the same size as you mentioned earlier. Okay, we don't disturb the size. So it will give you this result. And to make it more clearer, always use one more command here to make the image large. So already you know plt.figure and you write fig size equal to maybe 10 comma the image is not even, width is more, so maybe it will be 12,8 or 10,8. Let's see. Yeah, it is okay. So copy it and use it below for the others also. So here is the second image. Now it is more clear, these lines. So make sure you will have to work hard with these lines to make it perfect. Okay, and then I put over here for the last also the same. What I did, okay, sorry. So I have to go in step, run the M, and now. Okay, so this is the affine transform. So remember, affine transform I explained somewhere at the start. It produces a 2 by 3 matrix. So 2 by 3 matrix, but the problem with this transform is it has less low quality result. The performance is not so good. So you see over here, one, you can say that the three corners are in the correct position, but the fourth one, it is not. This is because the transform that it does, it is not perfect. It's not fully, it does not cover all the aspects of transformation. So affine transform has its weaknesses. For that purpose, we use the perspective transform. Okay. So remember at the start of the course, we mentioned somewhere that affine transform, warp affine, it takes a 2 by 3 transformation matrix, whereas warp perspective takes a 3 by 3 matrix. So warp perspective is the one that we will be using finally to solve our problems. So in perspective transform, the transformation matrix is a 3 by 3 matrix, and the straight lines in this case, they remain the straight. Okay, even after the transformation. Now for the images, this is important property that we always satisfy this property. So we in the perspective transform, we have a 3 by 3 transformation matrix, and straight lines, they remain straight after the transformation. And this is one of the major properties that is true for the images. So if there is a, for example, I just give you one example. Just imagine, just think, there is a picture, and in the picture you see the railroad, rail track. Okay, so rail track, when you will look at it, when it goes far away, it becomes smaller and smaller, but all the time in the picture, even it goes far away, still the two tracks or two sides of the rail track, they will remain parallel throughout the image. So this is one of the fundamental properties of all the images, that images, they have retain the straight line in the inside the images. All the things that have that are parallel, they remain parallel even after transformation. So when you want to do this transformation, this one is different from the previous one. Here we have to provide, to get the transformation matrix, we need to provide 4 points. We need to map 4 points between the input and the output image. So if you are able to provide these 4 points, then the image will be then the transformation matrix will be generated, and you can transform the whole image. And one more important thing is that out of these 4 points that you will provide on the image, 3 points should not be, any 3 points should not be collinear. So for example, these are the 4 points, so they are good. Okay, but if 3 of them, they are in the straight line and one of them is above, this is bad. Okay, so here what happens is that 3 are in the straight line, they don't give any important information. They are already in a straight line, they are representing only one aspect of the image. They are not covering, for example, other aspects of the image. So if an image is there, it has an object is a 3D object, so it will have some depth, it will have some x and y values. So you are only covering one of the aspect over here, which is not good. So it is not allowed that any 3 of the points that you map between the input and the output image, they are collinear. Collinear means in the straight line, they are linear, not allowed. Okay, so when you are ready, you have 4 points mapped between the input and output. Then what you will do is that you will perform the transformation. So transformation matrix, you can get it using get perspective transform. In the previous case, if you go back, we used the function get affine transform for the getting the affine matrix. Here for perspective transform, we use get perspective transform. Okay, so here you see some of the examples. So you see the same property for the perspective transform. After transformation or before, the lines will be, and the lines that are already parallel, they will remain parallel. So here it is. Okay, so in general, the general affine rule is that for any type of transformation, if it is uh, so this is the affine transform over here. The general rule is that I have got this matrix for transformation. So in the case of affine transform, we have a 2 by 3 matrix. Remember? So 2 by 3 means that we are using the overall matrix as a maximum size of 3 by 3. We are using only the top 6 elements. So each element, now this is important thing, each element or each value of this matrix, it represents 1 degree of freedom. Okay, so that's why we discussed that the affine transform, it has 6 DOF, 6 degrees of freedom. The perspective transform is even a higher thing, and in the perspective transform we have even, other than these 6, we have 2 more values. So in the case of perspective transform we have 8 degrees of freedom. The last value is 1. So 8 degrees of freedom there in the perspective transform. So general affine is this one, and perspective transform, it is this one. Perspective transform, and we also call it homogeneous transform, and there is another word used, it's called projective transform. So not homogeneous, it the better way is homography. So projective transform, homography, or perspective. So remember these names, important. Okay, so out of these things over here we are adding the 2 more factors over here for transformation, 2 more degrees of freedom. We normally call them keystone distortion. So they are producing some sort of distortion, or they are removing some sort of distortion. So this is, for example, your normal image. You can produce such a distortion that as if you are taking the image, and one side of the image you are taking it away from the viewer. So this is keystone distortion. So here I take this side of the image far away, the other is near to me. Whereas over here in this case, this side goes far away and the rest of the image, the top side, is near me. So this is perspective transform, and remember it is also possible in the opposite direction. Remember, in perspective transform and in all other transforms that we have seen, straight lines are preserved while we transform. So this is the summary. In translation, we have 2 degrees of freedom. Similarity transform, now you should remember this. Similarity transform is 3 types of transforms: translation, rotation, and what was the third one? Translation and rotation and scaling. So it provides 4 degrees of freedom. Affine transform is same similarity transform plus shear and aspect ratio transform. And the last one is the most powerful. It is called the perspective transform, or homography is a more common name. It has 8 degrees of freedom. It provides the keystone distortions also. Okay, so what's the purpose of this homography? It has more applications, it is more powerful. Here is one example. Let's say you have an image, and this will be your project also. Let's say you have an image, and image is taken from a side angle, and based on the points that you identify on the image, for example, let's say you identify 4 points somewhere, but no 3 points can be in the straight line, and then what you can do is you can mark them on the output image. So this is input, and you mark it on the output image, and you perform a transformation, and it will give you a feeling. You can easily transform the side angle view into a front angle view. Clear? So normally we will need 4 corresponding points to solve this transformation. What can be the use of this thing, transformation? What is the use of homography? It is something that is done actively. And remember, I told you that computer vision, it is something that is now, these algorithms, these things are in very close to us. We maybe don't know. So they are actively used in cameras. Any camera, either it's a professional camera or a simple mobile phone camera, they use these technologies. So homography is used. So for example, one of the example very common for this is the panoramas. So panorama, if you remember, it is the idea that you take, for example, you want to take a photo of a scene, and you want to take the photo over a wider angle range, more than the natural angle. Natural angle is you take the photo from the front, but for example you want to take a larger view of the you want to take a big photo of the whole 180-degree view that is in front of you, from rightmost to the leftmost. You want to take a big view, and you all know a panorama is created for this. So these days the cameras are very smart. You turn on the panorama mode and you just move the camera from left to right or right to left, and it will do it for you, panoramas. But in the old times also it was done that you will take 2 or 3 images, and then the mobile phone software will combine those images. Now if let's say I take 2 images, now it's not a joke that you just directly attach them together. So just directly attaching is not allowed. Why? Because both of these photos are taken from a different angle. So for example, this is the camera. One photo is taken from this angle, another photo is taken with a little bit, maybe very small difference, but a little bit different angle. So that little bit different angle makes such a change. Sometimes this angle can be very, very large, very different. So maybe you have 2 or 3 photos, so you can have big difference. So this change in the angle view, it does not allow you to attach them directly. So to attach them, first of all, you have to make them, you have to transform them so that they are in the same manner as if the photo was taken while at a 90 degrees perpendicular angle. So the photos that are taken from the side, they will be modified as compared to the front one, and then you will see that the images, they are transformed and then they are combined over here. Okay, so this is the application of perspective transform in daily life. So I hope it is clear. Let's now go for the lab work, how it works. So in the perspective transform, here is the objective. You need to do this transformation, you need to provide a 3x3 transformation matrix, and the important feature of perspective transform is that straight lines, they will remain straight even after the transformation. To find this transformation matrix, what you need to do is that you need to provide 4 points on the input image and also do the corresponding correct mapping on the output image. And amongst these 4 points, you already know, any 3 of them should not be collinear. Okay. Then the transformation matrix, when you can create is, you can get it from this function, get perspective transform. So you can do this, and then you can apply CV2 warp perspective. You can call this function with the matrix that you created. So let's go through this example. Now this is the same image, okay, as before. If you want, I can make it larger. Okay, so this is the image. So you see this is from a side angle, it's not good. Now I will mark out 4 points of the corners. The best idea, it's not done over here, because I think I take the points from above. So the best idea, before you mark the 4 corners, you should make a rectangle around this thing. Not a rectangle, an irregular polygon shape. So you will make the line around the boundary of this shape that you want to make straight. Okay, and then you mark these 4 points. So these are the 4 points. Okay, and important point is that what should be the result that you want. Result normally is such that you want the the points that are near you, you want to make them away from you and in parallel to the original ones. So originally this is first point. So the second one you want it to be in the straight line next to first one. So let's see over here. So first point is same. In the input and output image, first points are same. But the second point, it is 5 over here, but you want to make it 50. So the x direction, you want to make changes. Similarly, this point over here, so this discussion we already did it for the affine transform, same thing over here. So point number 1 will not change, 2 and 3 will change, and 4 will not change. Okay, so go through this, and I use these two set of points, points 1, points 2, and I will get the perspective transform. This is the matrix. This matrix over here is a 3 by 3 matrix, but you see it has 8 degrees of freedom. The last value over here is always 1. Okay, so the result will be this thing. The image has been changed, but you see the board itself, it is a perfect rectangle now. Okay, based on this, I will later on give you a mini project. I will explain it in a separate video. So I hope it's clear. Go through this theory. If you have questions, ask me. But before that, make sure you when you study these things in the presentation, you have to practice it yourself, and you have to practice on some other image. As always, I ask you. So let's say, so this is the board I practice with. What should be your so I don't have any image over here. So try to find some image on the internet that can help you. There is one image over here. This I will use myself. I will give you a demonstration for your project. So I will show you the example in that case. So this is an image. It's of a card that is a visiting card, and we will transform it using the perspective transform to make it straight. Okay, so here is the card you see. So I will make it straight, and we will see this. Okay, so see you in the next video where I will explain the project.